Welcome back to Physics 141 Online. Just to review where I left off in the last video, the first law of thermodynamics is a statement of the law of conservation of energy applied to the microscopic constituents of a system like a gas. And so it tells us that the internal energy of a system can only change one of two ways. And imagining that this system is a collection of gas molecules in some kind of container, those molecules can change their internal energy, the sum of their kinetic and potential energies, either by absorbing or releasing heat, and then, secondly, by doing work on a system or by having work done on it. And so the standard statement of this law of conservation of energy is that the change in the internal energy is equal to Q minus W, where we define, for the purpose of this equation, Q is equal to the heat absorbed by the system, so that means heat comes in, which would tend to raise its internal energy, minus the work done by the system. And the reason for the minus sign is that if the system does work on its environment, it loses some of its internal energy in doing that. So that's why Q and W are defined that way for the purpose of this equation. And then just to remind you that when we calculate Q and W for a particular kind of thermodynamic process, they can each be either positive or negative, right? If Q is greater than 0, it means heat is absorbed. If Q is less than 0, it means heat is released, which is the same as a negative amount of heat being absorbed, right? And the same way, if the work done is positive, that means the system does work. And for a gas system, that means it expands, it pushes on something in its environment. If the work is less than 0, that means that the gas was being compressed. And so those sign conventions are important to keep in mind. Now let's look at how work is calculated, because that's an important part of many of the homework problems that you'll have to do. So we would like to take the gaseous system and imagine that it moves from some initial state that's described by pressure 1 and volume 1 to another state described by pressure 2 and volume 2. And in the process of going between those two states, we'd like to know how much work it does. And we describe these kinds of things on a PV diagram. So to see the general expression for how to calculate the work, let's imagine this example of a gas that's inside some kind of a cylinder, and then it's enclosed by a piston, and it's in equilibrium initially, but then some force is applied to the piston, and it's going to compress it a very tiny amount, dx. And what we would like to know is how much work the gas system does in this process. And right away it should be clear that since this is a compression process, the work done by the system will be negative. Alright, so we can express this just going back to our definition of work as work is equal to force times distance, and the only reason we put the minus sign in here is because we're calculating the work done by the system. So minus F dx, and then the force that's applied to the piston, right, is balanced on the other side of the piston by the pressure times the cross-sectional area that the gas is exerting on the piston, and so that force is equal to pressure times cross-sectional area. And then finally we note that A times dx, that represents how much the volume of the system has changed, and so we can call this infinitesimal volume change dV. But when we do that, we have to realize that in a compression process the volume goes down, right? So A dx and dV have opposite signs. So that means that the amount of work done by the system in this process is P dV. If the volume goes up, then the work done will have a positive sign. If the volume goes down, then the work done will have a negative sign. And that makes sense. So what we can do is then add up the total amount of work done when the system goes between the two states indicated by P1V1 and P2V2. The one qualification for this is that this equation that we're going to write down only applies to what are called quasi-static processes. And what's important about that is in a quasi-static process, We are imagining that the process occurs slowly enough so that throughout the entire gas its pressure remains the same everywhere. If we were to hit the piston with a hammer very suddenly and it were to move very suddenly, there wouldn't be enough time for the pressure in the entire gas to equilibrate so that it's the same everywhere. And then that kind of a situation, we'd have to calculate the work differently. So we're imagining here that these kinds of processes are happening slowly enough so the gas molecules quickly adjust and maintain a certain pressure throughout the entire system. So if that's the case, then adding up all these infinitesimal changes in work or amount of work done means that we have the integral from the initial to the final volume of the quantity pdv. Another way of talking about these kinds of processes, besides saying that they're quasi-static, we can also say that they are reversible processes because the system stays in thermal equilibrium throughout the entire process. So this definition here, work equals the integral of pdv from v1 to v2, we will use over and over again as we study different kinds of thermodynamic processes. So let's move on now and talk about three special types of processes. You don't have to have just these types. There's lots of other things that could happen, but here are three special processes that happen often enough that we are interested in how to calculate the work. So imagine an isobaric process that happens at a constant pressure. System moves from V1 to V2. When I draw PV diagrams, I always put arrows on them because even though I should be able to figure out that the system is going from V1 to V2, sometimes the labels aren't that clear. And it's always good to put on your diagram which way the system is proceeding when it goes from initial to final. So, in this case, the work done is integral pdv, and since the pressure stays constant, p comes outside the integral, which leaves behind just the integral dv from v1 to v2, and that simply gives us v2 minus v1. So for an isobaric process, the work done, which you'll note is the area underneath the PV curve, right, is just P times the difference in volume, always V final minus V initial. So that's for isobaric. What about isothermal? We've talked about isotherms. An isotherm is a process on a PV diagram where the temperature remains constant, and according to the ideal gas law, we know it's going to have this characteristic shape of a hyperbola. So imagine an isothermal expansion here that's going from V1 to V2. How much work does the gas do? Well, clearly the work should be positive because the gas is pushing on its environment, it's expanding. Integral pdv, well, we replace P using the ideal gas law as nRT over V. And so since the process is isothermal, now here's the important part. We can take the T outside the integral along with the N and the R. And when we do that, we're left with a simple integral, dV over V. You've all seen that before, and that gives us the natural log. So the natural log of the volume then evaluated between the initial and final volume would be log of V2 minus log of V1, and that can also be written more conveniently as the log of the quotient V2 over V1. So that's an important formula for us to be able to use when we have an isothermal process and we want to know the work done. And lastly, what about an isovolumetric process? Here's a process where the system goes from a lower to a higher pressure, but remains at a constant volume in so doing. And you should be able to see, without too much difficulty, starting from the definition of work as integral pdv, that the work done in an isovolumetric process is zero. All right, hopefully you can see why that is. So let me move on then and just finish by showing an example problem that I'll work out in class where we will put these concepts into practice. Imagine that we have an isobaric expansion of 5 moles of helium gas. The gas is initially at 1 atmosphere in a container with 1 cubic meter of volume. So the gas, we heat it up and it expands to a volume 3 times the initial volume, 3 cubic meters, but it does so at constant pressure. So we would like to know the final and the initial temperatures of the gas, the work done by the gas or done on the gas, and the heat that the gas absorbs. And of course there's a conversion factor between atmospheres and newtons per meter squared that we'll have to keep in mind as we do the calculation. So we'll start as usual by plotting this on a PV diagram. We'll be able to calculate using the ideal gas law the initial and final temperatures. Then, from looking at the PV diagram, we can get the work, and then finally we can calculate the heat absorbed using the first law of thermodynamics. So that's the kind of problem that you'll have practice solving in the homework set that's coming up. So I will see you in class.